Welcome. Today I want to talk about the Planck scale on a computer. It's an exciting thing because we can experiment with it. Unlike the Planck scale which you have in the universe, this is completely ridiculous. It's away, too far away from anything. We can maybe get to 10 to the minus 20. Maybe I think that's if you look at the size of a quark or something. This is the scale which we have. This is a huge gap here. I mean, if you just look at the distance ladder, you kind of have a little bit of an idea. That's that scale here from the nearest star to us. That's about kind of what is missing here. So it's completely ridiculous to investigate this, and we probably will never kind of find out what happens on a Planck scale. But we can see what happens kind of in the scales we can measure, and we see continuum. But what happens in the very small, we don't know. But we can explore this on a computer. This is a larger project on Vietoris-Rips graphs which come from data which you have in a manifold. Take a Riemannian manifold, take a dense set, epsilon dense set, and look if the points are close enough, given by a delta. If they are close enough, you connect them, and so you get the graph, a finite simple graph. Under a very general condition, you expect this to be kind of has the same topology than the manifold, and that's mathematically. I express this using this notion of soft manifolds. It's a softer version than hard manifolds. Hard manifolds are manifolds where every unit sphere is a discrete sphere. I talked about this soft manifold. If you look at that, and if you look at the individual atoms here, they are not a nice crystal. They are a mess, three-dimensional structure. But what happens is every point is either contractible, you can take it away, or you have this kind of situation that if you puncture it, it becomes contractible. So that was the story which I talked about a little bit. I can just prove in dimension 1 that the Vietoris-Rips graph is really a soft manifold in that case. So every point will be contractible or be a sphere, and so we can actually, it's homotopic then to a cyclic graph. We can look at these graphs when we look at the machine graph of a computer. So the machine graph of a computer is defined by the vertices are all the points which are considered different on the computer. So if they're close enough, they are identified. That's all specified by some parameters which a programming language or a computer has given. So I have here just a situation in the GCC compiler of Mathematica. So you have a machine precision which is about 16 digits. So the same tolerance. And then you have about 2 to the 53 different machine numbers in the interval from 0 to 1. So that's about 10 to the 16 different numbers. The machine epsilon captures this a little bit. But then you have an equal tolerance which says, when do you consider two numbers really close enough so that you consider them equal? And that's larger. So that's this delta here. It's larger than the machine epsilon. And we can explore then kind of what happens. Say we take a number and we go a little bit, so how far do we have to go away until, not different, there are different numbers, but they are considered equal. I can run that if I take 1 plus 1.4 times 10 to the minus 14, I get that a machine tells me that these points are equal. So they are actually different points, but they are connected. So this is an edge in that graph, in that machine graph. And if I take a larger distance, if I go further away, then it's false. So that's kind of too large, it's no more connected. So what happens is now we are too far away such that this machine graph is no more, so that these 2 points are no more connected in that graph. So that's an interesting graph which you can explore. It's small enough that you can explore it. You can look, what are the properties, what are the vertex degrees, etc. But you can kind of already see here from this equal tolerance, because it's 2 to the 7 is 228. So this graph will have about 100 points in a unit sphere, 120 points in the unit sphere. But that's kind of what I was interested in, is this Planck scale. When does it really start to break, right? When do you have really you're no more in this halo, where now you're no more in that neighborhood which you consider equal. So you can experiment with that, and I kind of figured out last week what this number is, and it's actually this Planck scale is just 2 to the minus 46. So let's just look at this number here, 2 to the minus 46, and I take this number numerically. I have to make it larger. So that's 1.42 times 10 to the minus 14, 42, so that's what it is. Yes, that's about, it's not actually exact, that's not exact, but it depends on the point. So I was interested on how does this depend on the specific. Sometimes it's a little bit larger, sometimes it's a little bit smaller. Maybe I'll show you a graph of that, the graph I made a couple of weeks ago, which shows how that Planck constant depends on x. So I was interested in that. Also, it grows with x. We have to divide by x, and so that you see how that grows. But it's always close to that number. Not exactly, but it's close to that number. And I plotted that, and we see here the plot of this graph. There are two things I want to do. I want to first of all also show you here kind of these parameters which are in Mathematica. You can actually look at these parameters here. So first of all, there's the machine precision, which you can look up. This is all given always as a log, the log 10 of the actual thing. So 2 to the minus 52, and then you take the log, and then you have the internal equal tolerance, and you have the internal same tolerance. So these are things you can look up. And then there is also a minimal number. That's something different. That's when you look at floating point arithmetic. You can also look at, say, 10 to the minus 300, numbers like that. And they are also, but we are not concerned with this. Mathematica has pretty small dwarf numbers. These are kind of the smallest numbers you can really look at, also using floating point. But I'm not interested in that. I'm interested just in decimal numbers. And so you can look at this graph. So here's a little program which allows you to look at that graph. So what I do is I make a table of all numbers. Say I take here a table of all numbers 1 plus k over 2 to the 17. The vertex set consists of all numbers which are distinguished. And then I connect to, if they are distinguished by the same, equal sign means that they are the same, and equal means that they are equal. So it's a little bit subtle that you have to distinguish these two things, but you see that, look at that. So graph plot 3D of S. So this is, in this case, I took only 100 numbers, and so in this case, everything was connected with each other. So that's not very interesting. So let me just take a larger thing. Let's take 1,000 points here. So for 100, what happens? This was just below, too small. We were always in that halo. We were always kind of infinitesimally small. So that's kind of from the non-standard point of view. If you are a non-standard analysis person, you can see kind of you deal with non-standard models. Piano arithmetic, for example, we have numbers which are infinitely large. And so what I have here, I've taken 1,000 points. So you see kind of for 1,000 points, it already looks kind of a little bit. Let me just take 5,000 points to see that a little bit better. I take 5,000 points. And I run this here. Now what happens with 5,000, so this graph will be now much longer. This is kind of a part of if you're close enough, you're getting connected. But if you are further apart, then it's no more connected. This is, by the way, this is a discrete, I mean, if you would identify the endpoints, it would be a discrete one-dimensional soft manifold. There are lots and lots of actually, every unit sphere is contractible in this case, but you can take this away until you have a cyclic graph. It's actually pretty easy to see. You just take away points such that the distance of the neighboring points, the closest points left and right, smaller than 1. You can take that point away and you have still the same topology. So So you take that away until you can no more take anything away like that, and then you are, what you have is they are just neighboring points are connected, and you have a cyclic graph. But you can also take more. Let's just take a little bit, maybe more points. This is 5,000. Let's just take 10 points, 10,000 points. Then it will already be kind of longer. So be a longer piece of an interval. It's an interesting graph. It's not completely homogeneous. What is the vertex degree? So this is a list plot. I just look at the vertex degrees of this graph, and you see kind of there's a large set of points where there are just 128 neighbors. That's what you would expect, right, from that thing. But then there's at the boundary, of course, this decays, but it decays in an interesting way, and it decays differently on the right than on the left, which is related that you have larger numbers, and so things, the tolerance is getting a little bit different. So that was the original thing. I wanted to see how that halo depends on the point. So it's an interesting thing. I've not yet don't really understand completely the details of this graph, but it's something you can investigate. So for every computer you have such a graph where you take points, you take all the points which are possible to represent, connect to if they are close enough under some equal tolerance. And that's exactly what you have in a Vietoris-Rips situation. Vietoris-Rips situation. You have a manifold, you have a dense enough point set, usually kind of just huge amount of points. You don't care how large the dimension of this graph is huge, but you connect to if they are close enough. Maybe you take delta is equal to the square root of epsilon. So you take an epsilon dense set and you take the square root. And then you get the graph, which I suspect is just of manifolds. Oscar Lanford, my advisor, was very interested in such type of questions in the later part of his work. You know, what happens when you take a computer and you simulate something like a differential equation or a dynamical system? What happens? So you are dealing with finite objects, finitely many points, and you're cool. Let me stop here.